All right, we're going to start chapter 11 and we're going to talk about the unsaturated hydrocarbons. So when we talk about unsaturated, you got to remember your definition of saturated. Saturated means coated in hydrogens. So all of these unsaturated hydrocarbons have lost some hydrogens, but have gained other things. So for example, the alkenes have gained a carbon-carbon double bond. The alkynes have gained a carbon-carbon triple bond, and aromatics have turned into a ring structure that has basically alternating single and double bonds, but we'll talk about them in more detail later. So we're first going to talk about their structure and properties, and then we'll kind of talk about how to name them. So both alkenes and alkynes are unsaturated. Like we said before, they don't have the maximum number of hydrogens possible. So they lose some of their hydrogens, and in those place of those hydrogens, they double bond to another carbon atom. So the functional group, if you remember from your table, you're studying flashcards, Quizlet, something, those functional groups, is that carbon-carbon double bond for an alkene. And the way that I remember that is you see two E's, that means you must have two bonds between at least two carbon atoms. The alkyne functional group is the carbon-carbon triple bond. So you already know the alkane, now we know alkene and alkyne. So the very simplest alkene is ethene or ethylene. And that has two carbons, and those two carbons must contain that double bond. And then in order for carbon to have a complete octet, it wants to have two more bonds. So those two bonds are made by hydrogens, which give it the molecular formula C2H4. Now, if we go from that simplest alkene to the simplest alkyne, we're going to lose some more hydrogens, but we're going to gain another bond in between the carbons. So now we have a triple bond, but now each carbon only needs one more bond in order to complete its octet. So it would only have two hydrogens. So you notice as we go, right, this was our alkane. Every time we go from an alkane to an alkene to an alkyne, every time you do that, you're losing one hydrogen off of each of the carbons and giving that carbon-carbon interaction another bond. All right, so if we kind of compare some similar molecules, so we're going to take an example. This is all these examples are going to be having two carbons, so two carbons. So if you have two carbons and they're all carbon-carbon single bonds, you have ethane. If you add an additional double bond in between, we started with single, we're going to go to a double. You're going to lose two hydrogens, gain that double bond, and you will be ethene. You go again, you lose two more hydrogens, you gain another bond between two carbons, and you become ethylene. So ethylene, another way to say that is acetylene, and you've probably heard that acetylene torches, right? You've probably heard of that before. So when you look at these molecular formulas, what you're going to see is that every time we move from one category to the next, you're going to lose two hydrogens. So remember, our alkane formula is however many carbons we have, it's 2 times that number. So for example, here we had 2, and then we're going to add 2 more. So that would be, if you had 2 carbons, that would be 2 times 2 is 4, plus 2 would give you 6. So that's C2H6. As we go to an alkene, we're going to lose that plus 2. So now if we had 2 carbons, it would just be 2 times 2, and 2 times 2 is 4. And that's exactly what we have, 4 carbons in the molecule. So every time we move a category, we're going to lose 2 hydrogens. So the next one is 2N, so 2 times 2 minus 2. So 2 times 2 is 4, 4 minus 2 is 2. So that is C2H2, right? So you see the pattern. You can write those in condensed forms like this, and normally we don't draw the bonds, right? We just draw them that way. So if you see something written C2, CH2, CH2, you would look at that and go, I would hope you would look at that and say, oh, that doesn't really make sense, right? Each carbon only has 3 bonds. Well, if that is given to you in this format, then you automatically have to assume, right? There are 2 hydrogens attached to 1 carbon. There's another carbon with 2 hydrogens attached to it. What would give that molecule an octet on all of its atoms would be a double bond between the 2. So it's basically understood. So if it's listed that way, you can just leave it that way. It's okay. And leave that as the condensed formula. Same thing if you have a triple bond, right? If you just wrote CH, you're like, wow, that really doesn't make sense. But it actually does, because you think there's a hydrogen attached to a carbon, and then there are 3 bonds to the next carbon, and then that carbon's attached to a hydrogen. So in some instances, you can't, in some of the programs, like you can't draw the lines. So you just have to write the condensed formula this way. So it just depends on what you can and can't do. All right, so when we look at the structures of these molecules, what you're going to see is that when you go from an alkane, right, you see something that has that tetrahedral shape because it has 4 different things attached to it. It's going to be tetrahedral, and those carbons are going to organize themselves to get as far away from each other in the hydrogens as possible, and you'll end up in that zigzag pattern. But when we go to having a double bond, what actually ends up happening is these 2 carbons, and then the other 2 things that are attached to it. So the hydrogens here, and also this carbon, they are all in exactly the same plane. So we call this planar around the double bond. Now, it doesn't count for the rest of the molecule. The rest of the molecule is participating in carbon-carbon single bonds. And so you see that zigzag. When you go to a triple bond, what you see is that these atoms here, these 4 atoms, are all linear. They're all perfectly in line and in the same plane. And so you'll actually get some structural differences and chemical differences in how they behave because of this structural change. So if we look at those physical properties, kind of think that alkenes and alkynes are really similar to alkanes, right? We still have all carbons and hydrogens. So if you have all carbons and hydrogens, that's telling me that there's no real electronegativity difference, which means that they are non-polar. All of them are non-polar. So we got that. Well, if they're non-polar and water is polar, right, then the rule is like dissolves like. So it's not going to be soluble in water. So we have that. But if you have something that's a non-polar solvent, then yes, it would be highly soluble in that non-polar solvent. The other thing that you can look at is if you look at molecules that are approximately the same class, and all you do is change the weight or the size of the molecule, what you're going to see is an increase in boiling points. And remember, you got to remember this with size, right? As you increase the size, which is the same thing as the molecular weight, as you increase that size, you're going to have more and more electrons in that molecule. And remember how we said that the interactions between molecules depend on those nonpolar molecules, those London dispersion forces, and that they get these temporary dipoles when they run into things. So the bigger something is, the more electrons it has, the more London dispersion forces it can give. Well, if you have high London dispersion forces, you're going to have a high boiling point. So let's see if that holds true for our substances. Let's look right here, and this is wrong. This is from the book. This is wrong. It's ethene, right? Because we have a double bond. Propene, butene, right? They're all carbon-carbon double bonds. The last one's got it. Awesome. Okay, so we're going to look from carbon 2 to carbon 3 to carbon 4. Let's just stick with that for now. The only thing that's differing in these molecules, if we look right here, is that they're getting longer, right? They only have one carbon-carbon double bond, so they're just getting longer, so they have a higher molecular weight. So look what happens as we take that same trip and look at boiling points. For the small molecular weight, we have a really small boiling point, right? That's -100. But by the time we get to C4H8, now we're approaching 0. We're only -6, right? So this boiling point, right, is rising. This boiling point is rising as we see an increase in molecular weight. You can see the same thing when we talk about the carbon-carbon triple bonds. So if we take this little path and look at these 3 molecules, we have a 2-carbon, a 3-carbon, and a 4-carbon. And as we, again, go and look at those boiling points, it starts out really negative, and now we're positive, right? So it is rising again as molecular weight increases. Exactly what we kind of saw before. So now we're going to talk about nomenclature. Fun times. So you're always going to look for that parent chain, right? The parent chain is always going to be the longest continuous chain, but now that longest continuous chain must include the multiple bond. So the parent chain must include the carbons that participate in the carbon-carbon double bond. The naming rules are almost exactly the same, except that you are going to change ANE to ENE, right? Or YNE. If you had a carbon-carbon double bond, you would be ENE. If you had a carbon-carbon triple bond, you would be YNE. And you have to number the molecules from the end that will give that first carbon participating in the multiple bond the lowest number possible before you worry about substituents. So the first thing is always, when you're talking about numbering, worrying about giving the carbons in the carbon-carbon double bond the lowest number possible. Then you prefix the name of the parent with the number of the first carbon participating in the carbon-carbon double bond. I'm going to show you some examples and we'll talk through it. And then worry about substituents just like you did when we talked about alkanes. So let's go look at some examples, right? Okay. So if we have carbon-carbon single bonds, right? And this is going to be ethane. If we have carbon-carbon single bonds, but now we went up from 2 carbons to 3 carbons, right? We're going to have propane. Now, what if we introduce a double bond and we convert from ethane to ethene? What do we see? Well, you're going to give that same carbon number, right? This is 1, 2 carbons, so that's where we get the F. Then we know there's a double bond, it's E and E. But it just said that we had to number the carbon that participate, the first carbon that participates in the carbon-carbon double bond. Well, if you only have 2 carbons, they could both be carbon number 1. So you just don't put it. Same thing down here with propene. So you could number it this way, right? 1, 2, 3. You can't number it this way, 1, 2, 3. You can't, because you have to give those carbon-carbon double bond the lowest number possible. So you can't do those bottom numbers. But let's just say I took that molecule and I flipped it and I said CH3, I'm going to move that carbon-carbon double bond over. So I have a CH3, a CH, double bond, CH2. These two are the exact same molecule. There's actually nothing different, because I would have to go in and give this carbon number 1, this carbon number 2, and this carbon number 3. So it would get the same name. So even though the truth is it's 1 propene, we don't put the 1 because it's understood. There's no other way to do it. So when you see some without, there are reasons why. So when we talk about carbon-carbon triple bonds, this is the same thing, right? This is carbon 1, this is carbon 2, this is carbon 1, this is carbon 2. It doesn't matter, right? So when we go to a 3 carbon, if I even move that CH3, C, CH, I have to give this carbon number 1. I have to give this carbon number 1, 2, 3, 2, 3. It's named the same way because it doesn't matter where that double bond is, because you're gonna have to name it exactly the same. Okay, so let's look at a few more more challenging ones, right? Okay, so like leave it. Don't look at your answer yet. Don't look at your answer yet. All right, so you always want to find your longest continuous chain. You have to decide, are you starting here or are you starting up high? And it doesn't matter because they're both one away from that branch point. Doesn't matter. So let's just make it easy for ourselves and go across. Now our parent must go through the carbon-carbon double bond, and what we just did. Now, do I want to go up or down? And in this case, it doesn't matter. So I'm just going to go up for fun. And so now we have to start thinking about numbering and labeling. So if I numbered from this way, 1, 2, 3, 4, 5, 6, 7, that's one way I could number. Here we go, 1, 2, 3, 4, 5, 6, 7. So with this numbering system, the first carbon participating in carbon-carbon double bond in the blue is a 3. Whereas in the red, the first carbon participating in the carbon-carbon double bond is a 4. So I want to go with the blue numbering system. So I'm going to go ahead and get rid of the red, and I'm going to use the blue. Okay. So now I have to think about what are the other things. So this is a 3, right? This is where the double bond is. And I'm going to have 7 carbon atoms inside of my chain. So what's your prefix? Because you got to start trying these on your own. Don't just wait on me to do it. Go ahead and like pause the video or try to label them all on your own. I know y'all can do that. Okay, so when we do this, we're going to be 3, and then we're going to be hept because that is 7. And then the 3 tells us that we have a carbon-carbon double bond, but we have to put it E-N-E. We have to put it in the end of the parent chain name. So this is just our parent right here. So we need to also do substituents. So I have a substituent here and I have a substituent here. So I'm going to look at this and I'm going to say, okay, this is a 6-methyl and this is a 3-ME, 3-ethyl. So when we put it all together, ethyl comes before methyl. So 3-ethyl, that's where we got 3-ethyl. Then we got 6-methyl, and then we got 3-heptene. Okay. The more practice you do, the better you're going to get at this. All right. Next one. I could start here or here with my parent chain. I'm just going to start with the one on the top, make it a little easier. So we're going to go across until we get to a branch. No branch, we're done. All right. So just how do we want to number this? We can go 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5. Oh, I did the exact same thing. Okay, 1, 2, 3, 4, 5, 6. Now, here's our question. We have a blue number and I guess I did purple. If I look here, the first carbon participating in the carbon-carbon double bond is a 3 in the purple and a 3 in the blue. So for this one, does it matter? And the answer is yes, because I have another substituent. So this substituent down here, you want to give it the lowest number possible. So if we look, what are we going to give this? 5 is much bigger than 2. So we don't want to use these purple numbers at the bottom because it gave our substituent a much greater number. So we're going to stick with these. So this is a 2-methyl. And then our parent, right, at carbon 2, and we have a 6 carbon long. So this is hex. And then it's a triple bond, so it's YNE. And so if we put this together, this is wrong. That is wrong. It is 2-methyl 3-hexane. All right, good. Okay. Now, you can also have substituents that are halogens, like I guess I'm just trying to do the halogens. And when you do this, if you have a halogen substituent, wait and let those double bonds or triple bonds take precedence. So use those double bonds or triple bonds to know your numbering before you worry about anything else. So here's an example of one with a halogen on it. So you could have the numbering at the top, and let's do the numbering at the bottom and just talk about 2, 3, 4. So if I'm trying to give the carbon-carbon double bond the lowest number possible, well, on the top it's a 2, and the bottom it's a 2. Okay, so now we got to look at the substituent. Now we look at the chlorine and say what's lower, a 2 or a 3, and the 2 is lower, so we use the numbers at the top. Okay, so all you're going to do is say this is my substituent. It's on carbon 2. It's a chloro. Oh, CHLO. 2-chloro. Then you look at the parent. Parent's 4 long, so that's me eat peanut butter. That's the B, butene. And we said the ENE because we have a carbon-carbon double bond, and we're saying where is that carbon-carbon double bond? And it is at carbon 2. So we have 2-chloro, 2-butene. If we come over here, we can do the same thing where we look at the numbering. 3, 4, 6. So here's same thing. We have a triple bond starting at 3 and a triple bond starting at 3. So now, are we going to use the designation for our bromine group, a 2 or a 5? Oh, 5's too big. So we're not going to use any of the red numbers, right? We're just going to use the blue ones on top. So we have a 2, we have a 2 bromo group, and then carbon 3 is the first carbon that participates in the carbon-carbon triple bond. So we're going to end it in YNE, and we have something 6 long, so that's hex. Do as many of these as you can. Right. Here, this one's pretty easy to know which direction to go. If you look, here's the double bond, and look how much stuff's on this side, and look how much stuff is on this side. You're always going to start with the side that has less, right? Because it'll give that carbon, that first carbon that participates in the carbon-carbon double bond, the lowest number. So that one's kind of an easy one. Okay, and we look and we have 2 methyl groups. So we know we have something that is 8 long in the parent. 8 is the oct. We have a carbon-carbon double bond, so we're going to say ENE. That carbon-carbon double bond happens with carbon 3 being the first carbon participating. So 3-octene is our parent. Then we have methyl groups, and the methyl groups are at carbon 2 and carbon 6. So 2, 6 dimethyl 3-octene. So just keep doing them, and you're going to get lots of practice, and you'll be good. So sometimes you'll have molecules that have more than one double bond. So if you have multiple double bonds, just like if you have multiple methyl groups or multiple chlorine groups, however many you have, you call it, instead of calling it an end of ene, you call it a diene, or you call it a triene. But the triene and the diene tell you, okay, I have 2 carbon-carbon double bonds. I have 3 carbon-carbon double bonds, right? And it's the same rule for the alkynes. You would use the di, the tri as prefixes. Okay. So here's a diene here. All right. So if we look here, I'm going to assume you know how to number them. You know how to find your parent. You know how to number them. So I look here and I have carbon 2 that's participating. It's the first carbon coming in this direction. It's the first carbon that participates. And then carbon 4 also is the first carbon that participates. So we would say 2, 4 it's 6 carbons long, so that's the hexa. And then the di is telling me I have 2, and the E says double bond, carbon double bonds at 2 and 4. So 2,4-hexadiene. All right, let's see, which other one do I want to show y'all? Yeah, they're all pretty similar. So just do a little practice. I want you to look here at the cyclo. So remember that anytime you see a ring, I always kind of like when I say, okay, I'm naming, I'm going to go in and write cyclo. Like that's one of those things that I always write down that I know. Now, numbering on rings with double bonds can be a little bit tricky, but just remember when you're numbering that you have to go through the carbon-carbon double bond. So I wouldn't start here and go 1, 2, 3, because as I'm going this way, I'm not going through the carbon-carbon double bond. That's why we start on this side and we go 1, 2. So as we go in our parent, we go through the carbon-carbon double bond. Okay. Now, could you have started here? 1, 2, 3, 4, 5, 6. Yes, you get exactly the same answer. So there's more than one way to do some of these. So this is a cyclo, and it is 6 carbons long. So that's where we get the hex, right? And then we have 2 carbon-carbon double bonds. So this is cyclohexadiene, right? Now, before we do that, what numbers are the first carbons that participate in the carbon-carbon double bond? So we call that 1,4-cyclohexadiene. Then you have to name whatever is another substituent, and so we have a methyl at carbon 3. So that gives me 3-methyl 1,4-cyclohexadiene. You're gonna sound so cool, so smart when you can say all these. All right, when you name cycloalkenes, just like what we did just then, just prefix the parent name. The parent name with cyclo. That's it. And just like we said, you have to start at one end of the double bond and pass through the double bond for the numbering to be correct. And then give any of your substituents a lower numbers as you can. So if we zoom in on this molecule, right? So here's a substituent, here's a substituent. And if I looked at my longest continuous parent chain, so I have to go through a carbon-carbon double bond. So either I'm going to start here or I'm going to start here. So let's go one way and see what happens. Okay, so I'm going to say this is my 1, 2, 3, 4, 5, 6, because that was my continuous chain going all the way, right? Now, what's the other way that we could go? Well, I could go 1, 2, 3, 4, 5, 6. So if I did this numbering this way, it would still be carbon 1 and carbon 1 that participate, so that's okay. But look here, we have a 4 and a 5, and we have a 3 and a 6. Go with the smaller number. So all the outside numbers are good, and we will erase our inside numbers. So when we talk about this, why does that say 5? 1, 2, no, it's a 4. Ooh, absolutely. Okay, so as we go around our ring, right, we go 1, no, have to. Okay, we have a 4-chloro, and then we have, coming off of carbon 6, we have a 6-methyl, right? So we have a 4-chloro, 3-methyl. Now don't forget, lots of people forget this little part, cyclo, and then because we have a 6-long parent, we call it hex, and then it's hexene because we have 1 carbon-carbon double bond. So not bad, just lots of practice. Okay, this is the last section we're going to cover today. And the question is, so we have all these carbon-carbon double bonds and triple bonds. What is the result of this? Well, when we had only single bonds, there was free rotation of every atom in every different way. But once you add an additional bond and you make a double bond, it's rigid. You can no longer rotate about a bond. And so because you are going to have restrictions like that, it's going to result in what are called cis and trans isomers. So if you talked about cis and trans isomers, here's two carbons. Let's say they're participating in a carbon-carbon double bond. Each carbon can bind to two other things. So we'll call them X and we'll call them Y. Doesn't really matter. So in order to know if you have something that has the ability to be cis or trans, you have to have a different group on each of the carbon atoms that are attached by the double bond. So if we look first at this green carbon, we can see that it has an X and a Y attached to it. So yes, it has two different groups attached to it. Then we look at the second carbon and we say an X and a Y, and yes, it's two different things attached to it. So yes, we can identify if this is a cis or trans isomer. And the way that you do that is you look at the things that are attached to the carbon and how are they in relation to, we call this the plane of the double bond. So the plane of the double bond basically goes through like this. And what we would say here is this is up and this is up. See how each of them are going up? Then that would be a cis configuration because it's the same. Cis is always going to mean the same. So what if instead of what I had there, I had an X and I had an X and a Y and a Y? What would happen? Well, if you kind of follow the X, right, you have one going up and one going down. So this is opposite. So this is trans. Yeah. Okay, and I'm going to show you some more examples. So if you look at an alkene where you can have two different groups, so this one has two chlorines attached to it. There are two different ways that those chlorines can be attached. Either they can be on the same side, which would be two down or two up. So Cl, Cl, H, H. Both of these two structures are exactly the same. You just kind of flip them in 3 dimensions. So if we look at these, we can see that these groups are both well below the plane of the carbon-carbon double bonds. You see how they go down and they go down? So that would be a cis configuration. And then you have to say what's on what carbon. So we go 1, 2, it's only 2. And each chlorine is attached to the parent carbons. So that's 1, 2, dichloro, and then we only had 2, so that's ethene, right? Not too bad. Now, look at the next one. We're comparing our chlorines. Where are our chlorines? Now, oh my gosh, this is the plane of the molecule. I can see that one of these chlorines is going up, one of these chlorines is going down. And so that gives you the opposite. That's what trans kind of means, is opposite. And so the trans configuration is possible because you have those two different groups attached to the carbons participating in the carbon-carbon double bond. And we can look at their orientation. So we have a trans 1, 2, because we have 2 chlorines, dichloro, and then this is ethene, right? So do some more practice. So here are just kind of some good rules for you. If you're going to try to identify something that is cis or trans, if one end of the carbon has 2 groups that are the same, then cis and trans isomers are not possible. So you couldn't do it. When we talk about those carbons, they have to have different groups attached to them. And an easy way to know if it is up and up or up and down is to find the carbon atoms of the parent chain relative to that double bond. And if the parent chains are both on the same side of the double bond, then they're going up and the molecule is, they're both going up and the molecule is cis. If it's opposite, then the molecule is trans. So let's look at kind of a few different ones. So here I'm going to highlight I need a little bit lighter color. Okay. My main chain, I got to go through. Main chain is always going to go through a carbon-carbon double bond or a carbon-carbon triple bond. So now I'm going to look at the groups that are attached to my molecule. I have a chlorine here. Then I have a chlorine here, right? Ooh. Okay. Right. So I have two groups. So I know I'm going to have to number these carbons, and they numbered them wrong. Okay. 1, 2, 3, 4, 5. So this is a 2 and 3. 2,3 dichloro. So the chlorine is at carbon 2 and the chlorine is at carbon 3. So that's 2,3 dichloro. And then my length is 5 carbons long. So that's pent. So that's pentene, right? And that occurs. This 2 is just telling me where this carbon-carbon double bond is. So it's the first carbon that is participating in the carbon-carbon double bond. Now I just need to say that chlorine, one chlorine is going up, one chlorine is going down, and that is a trans configuration. So when we look at compounds to determine this, you're going to have to first find the parent chain. So I'm going to start up here, and I'm going to go through the carbon-carbon double bond, and then, oh, this looks longer. We're going to do that. Okay. So my question to you is this cis or trans? Well, this one's going up and this one's going up. So that must be cis, right? Must be the same, cis. Now, look at the next one. This one's a little bit harder to find that parent. I start down here. It's the only real choice we have there. Go through the carbon-carbon double bond. Now, what do you notice? It doesn't matter what you identify as parent. Let's just say that's parent, right? What else do you have? Here, I have a 3-carbon group that's attached to the parent that's attached through the central carbon. Look at this. It's a 3-carbon group where the middle carbon's attached to the central carbon. Look at that. So the first one was cis. The second one is no cis or trans because these two are the same. So even though they're more complicated, it doesn't matter. If they're the same, then you don't indicate cis or trans because it wouldn't matter. Okay. So here I'm going to look at my parent. It's 2 on either side, so it doesn't really matter, right? And there we have, it looks like both going up. So if we look here, we go up and we go up. And so this is cis, right? Do some more practice. Okay, last little bit. We're talking about fatty acids. Fatty acids are an example of places where we see a lot of unsaturation. So you can see this in the foods that you eat, right? You know, it's this many grams of saturated versus this many grams of unsaturated fat. And so why are they different? It's because they behave different. So if you think about this, fatty acids have long chains of carbons and hydrogens. And here we have a carbon-carbon double bond, but it's still carbons, hydrogens, until you get to the very end. And the very end, you have some carboxylic acid functional groups. So those do play a role, but we're not going to talk about them super extensively until we get to kind of lipids. So what I want you to think about is in your cabinet at home, right? You have some vegetable oil. And at room temperature, what kind of substance is it? It's a liquid, right? If you go get your vegetable oil, it's a liquid. But if you look at something that's an animal fat, like butter, it is saturated. And therefore, at room temperature, basically, you're a solid, right? So we know that there's a difference in melting point and boiling point for all these substances, depending on what configuration they have, right? So this is an example of a cis fatty acid. And what you can see is that these double bonds create basically like kinks inside of the chain. And so normally if you had something that was unsaturated, if you had a tail of unsaturated fats, right? Then what you would see is these tails line up absolutely perfectly with one another, layer after layer after layer. And so this is an alkane, and it has lots of London dispersion forces, right? So it's going to have a really high boiling point because each layer of those hydrocarbons is going to fit really nicely on top of the other. Think about it like pages in a book. They lay perfectly one on top of the other. But then when you get something with a double bond, something that is a cis, in this case, fatty acid, what's going to happen is instead of having that perfect alignment, right, you're going to have some places where you're going to lose some of the interaction, right? And so that difference in how much each individual strand will associate with another will tell you its boiling point and melting point, right? The more they interact, then the higher the boiling point is going to be. So if we talk about fatty acids, it's really important to kind of talk about cis versus trans in our diets. Basically, we've been eating cis fatty acids for a long time. So our bodies know how to handle that. But trans fats aren't quite so highly regulated. And so if you have too much in your diet, you can it's actually detrimental for you because you don't have the enzymes there to metabolize the trans fats. And so they lead to unhealthy consequences. For example, having lower levels of the good cholesterol, the HDL, and having high levels of the bad cholesterol, the LDL. So just having a certain kind of double bond actually has a huge impact on the molecule, right? And so if you look at the difference, what you can see is if you're following this parent chain, follow the parent chain, and then we're going to kind of zoom in and we're going to see here, parent chain is going down here and it's going up here. And so you know that that is a trans fatty acid. Okay, we will pick up the rest next time I see you. All right, have a great day.